so much for this opportunity. I'm going to talk about some of the work we have been doing in how AI and connectivity can be brought together. And we are using robots as an example, but I think this kind of technology has a lot of other applications also. And towards the end, I'm going to talk a little bit about ARTPARK, which is an incubatory which we have set up, just to kind of give you also a sense for, besides some of the academic research work we do in IISc, we are also doing some of this incubation activities. So I just want to, in this slide, share my perception of how the AI capability is evolving over time, right? And this is something where we are currently. AI is very good at, giving you answers to specific questions of interpretation and so on. And it has become multimodal, as we saw also in the previous talk. And we have reached or exceeded human-level capability in understanding images, perhaps even text, speech, and so on and so forth, right? So this is where we are right now. And of course, these models take huge amount of compute to actually train and make. And this is current state of the art, right? What we are good at as humans, we are also very good at planning, and especially long-term planning, right? Planning for 5 minutes, days, months, years, decades, right? So we are very good at that. And I do believe that AI and robots will actually also, that is kind of the next thing which people are already working on, how to kind of bring in kind of more longer-term planning capability into these robots. And final, I would say the frontier in some sense is teaming, collaboration, and so on. So as humans, we are excellent in working with others, at individual level, group level, organizational level, country level, et cetera, right? So we have this ability to work with each other. And I think that is very critical if you want to do and make big differences. And right now, the AI technology, if you see, whether it's at the robot level or at LLM level or whatever, it's largely individual, right? There's an individual entity which is actually answering or doing stuff for you. But going forward, having robots work with each other. By the way, I'm using the word robot as a proxy for an AI agent, but an AI agent in the embodied form is something which is basically a robot. But you do not all the time have a body. So collaborating AI agents, as well as humans and AI agents working together in a collaborative way, that is going to be really interesting. I mean, there's a lot of interesting research, technical challenges, but I'm also very optimistic that there'll be a lot of practical applications out here. So, and if you look at the AI systems, right, which have been built, and again, this is my perspective of how I think they will go forward over the next few decades, right? So, this is the current, if I were to use the word the classical AI system, because in this AI world, things become classic in a matter of 6 months or so. So excellent at inferencing. You train the models, trillion parameter models, and you ask them questions, and they're able to kind of give you answers, right? And what is the next step is actually bringing in the planning capability into these AI systems, right? So you're not just asking a question, you're giving it a task. And you say, okay, do this task for me, right? So for example, to take off from the previous speaker's really nice talk, credit score is on the left side, right? Put all the inputs, I get a credit score. But now I want to kind of follow through with the process. I want to actually give a loan to the person. I want to track the person, maybe help the person, handhold the person through the life cycle or the journey of them, going through what they said they will do and help them, right? So that is really the planning, and which we as the human agents are excellent, but That's where we want the robots or AI agents also to be able to do. Finally, to actually do it in a more effective way, we are excellent at building models of the world, right? And our models are always updating, models about ourselves, about others, about things around us, and so on. And that is really what is a digital twin. A digital twin is actually a live model which keeps getting updated based on whatever sensory inputs, multimodal sensory inputs which are coming in, which then become very critical for us to do better planning and execution. So, so our own work, my own work, and some of the work in our group is actually focusing on these aspects of creating digital twins and including them as part of this multimodal systems to help with planning, decision making, decision support, and so on. So what I'll do is give a snapshot of some of the things we have been doing. And I have to say that it is work in progress, and we have just started it. And I think there's a lot of things, at least I don't understand, and I think there's a lot of opportunity to kind of really innovate and also do research in. So one of the interesting technologies which is accessible to machines and robots, which is not that, I mean, we do have access to communication systems, but not in the way in which machines can use it. And this is very critical, as I said, because I see in the future collaborating robots, collaborating systems with humans and robots and so on, right? And that is really because of 5G and the intelligence and the support which comes from the cloud. Now, one of the things for us as humans is that, yes, we can communicate with each other and collaborate, but our latency is much larger, right? I mean, it's like half a second, 1 second, and maybe even like minutes, hours. So we cannot break that barrier, right? We cannot run at a millisecond level of interaction. But with machines, you can, right? I cannot very easily use your brain's compute to solve my problem. I mean, I can do that by asking you a question, asking, et cetera, et cetera. I mean, but again, as I said, the latency is much more. But with machines, which is a nice thing, but also a scary thing, is that you can actually bring to bear the world's entire compute to solve some problems, and which can be also a little scary in what can happen, right? And so you have this hierarchy of compute and capability possible, right? I mean, you have this compute at the edge in the robot, and then if you have these devices in enterprise, like in this Hilton or in your company or whatever, we have a local network and on-prem compute also you can put in. And then, of course, you can go to the cloud, right? And you have the supercomputers, high-performance HPC systems sitting there which can crunch and do more things for you. Excuse me, sorry. So, so this is a hierarchy which, as system designers, we can and we should take advantage of as we design our systems, algorithms, etc. Right? And I want to kind of give you a simple, one example of how we are using this for our robots. But of course, it's just a tiny example, and more can be done, right? And that's what I'll start off with, what we call a third eye for better localization for a robot, right? It's basically, if I can see through your eyes also, can I do things better, right? And that is possible because of the capability of connectivity which is there, low latency connectivity. The second thing is, as we are, I was talking about building these models of the world, the digital twins, and having these models be overlaid with semantic information allows them to then to be coupled with reasoning and planning tools like LLMs, right? So you can actually then have your digital twin be used by an LLM and work on by an LLM to come up with more, interesting semantic plans. And finally, I'll just, as I mentioned, talk about some of the innovation activities which we are doing, right? So the problem is, just to kind of illustrate this very specific problem, the problem is you want to know where a particular robot is, right? You can also think of this as a problem where you want to know where a particular individual is. Imagine that you have a retail store and like a mall, like the Mantri Mall or any of these malls. You would like to know where people are, and people would also like to know where they are. The GPS doesn't work inside, right? So what can you do? How can you improve the How can you build an equivalent of a GPS where you don't have satellites, right? And that information is, of course, extremely important for robots, but also there are a lot of other potential use cases involving people and not necessarily robots. Typically on a robot, the way this kind of problem is solved is what is called SLAM, right? Simultaneous localization and mapping, where the robot, as it's going around, just like us, we build up a map of the world around us. And this map also has metric information. I can know where things are, what is the distances, and so on. And then I can use that to both plan my path as well as know where I am, right? And this is a typical kind of, very high level 2 blocks, what is called a visual SLAM that is based on images you can know where you are. And also what is called some filtering technique, extended Kalman filtering type technique, which is used to fuse information from multiple sensors to have a better estimate of where you are. Now, that is what a single robot will do, but imagine now I have a robot in a place like this, and I have a lot of cameras already around. I already see a few cameras up here, and I also have a 5G system, right? So now I have other eyes out here. How do I use information from these other eyes to help my localization, right? So that is basically the problem. And why I think this is kind of interesting is that many of these enterprises will have edge compute, on-prem compute available, so you can do a lot of this heavy-duty AI-type processing out on the compute and make that available as a service for your systems in your enterprise, right? And so what is the actual compute you need to do? You need to take this data coming from multiple cameras, which are fixed, as well as in your robots, fuse them, and use that to kind of really estimate, okay, this is where I think you are, and the robot uses that further to fuse it with its own internal knowledge, and then comes up with the final understanding of where it is. And I won't go into too many details of all the steps which are involved. You need to kind of be able to detect a robot, because your cameras, you have to distinguish between a robot A, robot B versus a chair versus whatever else. You need to be able to track the robots across multiple cameras. You need to be able to associate. You're saying, okay, this track corresponds to the same robot which I saw in this other camera track, right? So association. So these are the 3 problems you need to solve, and then from there you have to estimate. And all this has to happen very fast, right? Because as the robot is moving around, you have very little time. It has to happen within 30 milliseconds or 60 milliseconds at most, which is the frame rate for a video, right? So you need very efficient implementation. Again, it's a little bit of busy slide as to what we have done, more precisely my student has done. I will not go into all the details out here, but a lot of the building blocks are well known in the robotics and image processing community. It's to how do you combine them with some of the deep learning based approaches, and so where you actually use some of the AI models to extract certain information, which you then use with standard classical computer vision techniques to localize a robot, right? Just to kind of tell you how it actually looks, you see those robots in different situations, and you have these little red dots you can see on them. Those are specific points on the robot which are identified, and which helps us to kind of localize the robot. And the goal is to make this whole thing very robust, which can work under dark conditions, different backgrounds, different poses of the robot, etc., right? So this is a robot which we have used, on which this kind of thing was tested out. And this is a little busy table, but I think that the message out here, what we wanted to convey is that, each of these numbers are around the average error, which is like about less than a centimeter. These units are in centimeters, so it is a pretty good localization of the robot. And this is just, this is what we do in research, is to try different things and try to understand. Whereas in industry, once it works, you just move on. Here we need to kind of really figure out why it works or why it doesn't work, how does it compare with other approaches and things like that. But the message out here is that just with cameras, you can actually do very good. You don't, typically in robotics, autonomous vehicles, etc., you also have LiDARs, which provide you with very good precision, but with some more advanced image processing and, AI-based techniques, you can actually also do away and get better performance with just using cameras. And more cameras you use, the better it is. So that is the basic message out here, and you can get very good performance out here. Just a very, kind of in the lab, the student put together, just to show how this kind of infrastructure can help you, right? So what is out here is that there is this robot, and there are a bunch of stuff thrown around in the floor like a typical teenager's room, and the robot has to kind of navigate around. And the problem is the robot doesn't have its own eyes. Okay, it has a LiDAR, but the LiDAR is a 2D LiDAR. It can't see the objects on the floor. And so when that happens, the robot on the left is actually trying to make its way without hitting things, but it's not very successful because it's not able to see things below its eyesight. But because there is the robot on the right is actually using information from the camera which is outside, that is being fused to form, and help it better, right? So it's now able to use that and do a much better job of avoiding all the obstacles. This is a very simple illustration of how seeing from someone else's eyes can actually help make my design of my system much more robust and better, right? So, taking this kind of concept, right? Here the idea was to just, the information which I wanted to get was state of where the objects were and, what is the robot state. Now, we kind of want to generalize this more and kind of create a digital twin of the entire environment, right? And again, you have all these cameras, you have, people, and you have other signals which you're getting, and you want to kind of be able to fuse all of that information, right? And the point here is that we have communication network everywhere. So that is the beauty now, is that you have communication network all over the place. Everything is connected. And 5G is going to give you even lower latency, 6G will be even better, and so on. And so the idea is really to kind of use this to build up a model of the world. And the model should be live model, which you can then use for multiple downstream applications, right? So again, use the edge cloud in an enterprise to actually do all your compute to build these models, and these are live models. I know where people are, I know where objects are. I can do things like, for example, decision support. The enterprise operation can take advantage of this internal representation and say, okay, this is what I should do. Safety alerts. Someone is going into an area which they are not supposed to do, and you can automatically raise an alert. And of course, autonomous robots can get benefited. And you can do a lot of what if I did this, if I change this, what will happen? A lot of those kinds of things can be done, right? So that is the intent of these kinds of digital twin technology. Now, the digital twins is a very big buzzword, catchword, and there is no single approach to build digital twins, right? People have been talking of digital twins for the past 15, 20 years, and there are various approaches and very problem specific. You can take a specific problem and build a twin for that particular problem, right? So here we are trying to kind of say that, look, we want to kind of create is there a general framework, general platform by which you can build twins which can serve multiple downstream use cases, right? So one of the use cases is around being able to visually see what your scene is. For example, a construction site, right? A construction site, as the building is getting built, the manager or the planner, they want to be able to kind of walk around and see what is going on, whether things have been built properly or what is the status and so on. So visually rich twin, is clearly something of value there. In addition, being able to augment such twins with semantic overlays, like I said, right? And I'll give you an example of that. Helps you to kind of interact with the twins and ask a lot of questions at a level where, as a human, you can interact. So one of the interesting technologies which emerged about 4 or 5 years back is this concept of radiance fields. And the idea was to build a representation of the scene by fusing information from multiple images taken from cameras from different poses, right? And it was a very interesting approach which actually created a lot of buzz and a lot of people and a lot of derivative work after that. And what are called neural radiance fields, and the radiance fields radiance field is basically at a particular XYZ, what is the intensity of light there, right? You can think of it that way. What is the color? So that whole thing is, you can think of it as a function which gives you put in XYZ and it will tell you what is the value of the radiance field there and what is the color. And and the idea is to kind of synthesize or train such a function using neural nets. As you know, you can approximate any function if you have enough parameters in a neural net, right? Following that, there has been a lot of explosion of work out here, and one of the new techniques is what is called Gaussian flatting, 3D Gaussian flatting, where instead of this kind of implicit function which is representing, you can think of actually pixels or voxels, right? But the voxels are a little special. They have the shape of a Gaussian balloon. And that is kind of useful to be able to kind of render all kinds of images. And it turns out that there are some benefits of using this kind of explicit representation of the world using Gaussian bubbles. It allows for fast rendering, but more importantly, you can also overlay now semantic information much more easily on these Gaussian bubbles. So what do I mean by that? Right? Imagine that you have this scene out here. I mean, in this picture out here, for example, there is this scene, and you're asking the question, where is the chocolate donut in the scene, right? Now, of course, there are 2D, kind of AI models which will allow you to do that, but here we are talking of doing it in 3D, right? It's a 3-dimensional representation, and that is important because maybe we want a robot arm to go and pick up the chocolate donut, right? So you need to know where exactly in the 3D space it is in. So that is where it's not just a collection of points or Gaussian bubbles and so on. You also need to have a notion of what is the semantic organization of the information out there, right? So that you can do various downstream tasks out here. And 3D is very interesting because it allows you to kind of do things which you couldn't do in 2D. For example, on the image on the center, there is a toy, and you're asking where is that particular toy, right? If it was just a 2D image, you would not be able to know the toy because the image on the left, the black and white image, the toy, only a portion of the toy is seen, right? A little arc, because it's occluded. Okay, and the zoomed version is shown on the right side. But as soon as you go to a 3D, what happens is that in a 3D, you would have probably taken the image of the same toy from a different angle at some other point, right? So that having that, you have seen it somewhere, so you can kind of have that information be part of your internal representation. And now you can actually, the system can actually, if you use 3D, it can actually answer the question better. Okay, that toy is actually hidden behind this, but I can see it from a different perspective, right? So that's where, kind of a 3D representation of the world, right? 3D digital twin becomes very, very interesting and powerful. And the point is to overlay that now with semantic information. For example, here on the left side is a teddy bear, and the right side is, that teddy bear is actually segmented out, right? And this is very kind of, just to give you one example of how it can be used, so this is some work done again by some of my students. On the left side is as the robot is moving, it's taking pictures and is building an internal representation, right? There are 2 laptops, there is a book, physics book, Resnick and Halliday, and then the robot moves, and now the robot is only seeing that in the center image, it's just seeing a laptop. Right? Now you ask the question, you can ask a question like, okay, can you get me this physics book, right? Or you can ask even more complex question. With the LLM technology, you can kind of, knowing what you have, you can pin it down and say, yes, there is a book, Resnick and Halliday, and I need to get that. And the important point is, in this 3D point cloud, you can localize and say that the third image is actually saying, okay, this is where the Resnick Halliday textbook is lying in the 3D space. That then can be used by the robot to actually go to that place. Also, the robot might have a hand to manipulate, pick it up, etc., etc. A lot of downstream things can potentially be done. So, again, as I said, this is work which is right now kind of, a lot of people are working on similar things, and it's work in progress. So just to summarize and kind of look back at what I kind of described so far, is that we should take advantage of connected systems because it opens up additional dimension, which you can kind of then think of distributed processing and computation. And of course, AI technology is critical, and especially Gen AI, when you want to do planning and so on. And it will have huge impact on multiple verticals, as all of you already know, right? And the point here is that anything you invest in the infrastructure to support that, you can amortize over multiple applications. And so I think it will pay off as you go forward, especially when you have multiple agents, multiple robots working together, right? And because of privacy reasons of data and bandwidth issues, it does make sense to have on-prem compute, which can do a lot of these things. Also, more importantly, from a latency perspective, right? You can have systems which are very reactive and which can do these things. And of course, I am very optimistic. I think but having said that, there are a lot of still open questions. What is the right way to represent information? I kind of mentioned about neural radiance fields, Gaussian splatting. They're not by any means the last word. And also, you kind of want to do these systems which there's modularity, right? I should be able to buy a digital twin model from some other company and use it in my system, right? So how do you make composable modular twins? I think that is still an open question. And there are certain other interesting technical questions as you go forward. Of course, data is critical for all of these things. And at least from ISC side, we are always looking to see if we can partner and make a lot of these data sets available as open data sets for the community to use, right? So I'll just take a few last 2-3 minutes just to explain this new entity we have created called ARTPARK. It is an incubatory, which means it's an incubator plus laboratory, right? And we are really looking to support startups and innovation teams, which want to build off AI and robotics technologies to create new solutions. And the reason we set this up was we saw this gap. On the left side is research, right, which we do in academic labs, etc. On the extreme right is products in companies like you are from, probably you create products and commercialize. But in between, there is a gap, which is the innovation gap, right? Where you have to kind of take a lab level idea and really figure out what is the right product market fit for that, which means understanding, identifying customers, talking to them, etc., etc. A lot of things happen, which typically a startup is a good vehicle to do that. But we want to even support even earlier stage, before you even start a startup, pre-startup, right? So that is the kind of stage which would really like to support teams to kind of take a TRL3 lab level technology and take it to a TRL6, pilot scale product prototype, working with potential customers and showcasing them. So in that journey, and really looking at deep tech, which requires quite a bit of investment and handholding. And hopefully by that time, the startup can get good valuation and raise VC money and take it forward, right? So that is really our mission, deep tech innovations. And this is set up, of course, by ISC, but with seed funding from both Government of India and Government of Karnataka. And it's set up as a not-for-profit. And we have taken this view of, to do this, a thematic, kind of an approach. We call it the hourglass model, right? We have thematic programs in multiple areas. For example, robotics manufacturing was an area. We have a number of startups there. We have now a thematic area in wireless 5G use cases. And a bunch of other thematic programs are in the pipeline. We are working on it, right? So we really look forward to collaborations with startups, small companies, big companies, etc., etc. So because it's set up by ISC as a not-for-profit, we can also engage with government. So it can be a really nice triumvirate of academia, government, and private enterprises working together. Physically, we have a big, we call it Art Garage, like to kind of inspired by the Silicon Valley garage startups, right? This is one of the HMT factories we have taken, and inside that factory, we have set up the technology platforms. There's a 5G test bed. We have data platforms for health data, speech data, etc. And now we're kind of building up as we go forward many of these facilities. Just some of the startups which are right now incubated, they're about a year and a half old. Comrado is like a drone startup, 400-kilometer range drones, autonomous charging systems for drones, AI autopilots, etc., etc., walking robots. And, the one in the center, Flow Mobility, is building, you can think of it as autonomous wheelbarrows for construction sites and so on. So these are the various startups, and hopefully, as I said, we look forward to collaboration. So please reach out to me or anyone in ARTPARK. Thank you very much for your attention.